Hello, future engineers. Here is another video on rotated vessels. I hope that your knowledge in analyzing rotated vessels will increase through this problem. A closed cylindrical vessel, 2 meters in diameter and 4 meters high, is filled with water to a height of 3 meters. The airspace is subjected to a pressure of 100 kilopascals. If the vessel is rotated about its vertical axis through 150 revolutions per minute, determine letter A, the location of the vortex below the bottom of the vessel. Letter B, the maximum pressure that can develop within the vessel. And letter C, the exposed area of the bottom. Letter D, the force on the top cover. And letter D, the force on the bottom cover. So let's draw the figure. So this is the overall figure for this problem. But first, let's compute the height of the paraboloid where the vortex exactly forms on the bottom center, and it is represented by this white dash curve, parabolic surface. And the formula is derived in my other videos, preceding videos, especially the lecture video. Height of tank square over 2 times k, where k is 1, the empty depth of the right circular cylinder, which is 1. So 4 square over 2 times 1. So that is 8 sub v. So substitute 4 square over 2 times 1, and it is equal to 8 meters. Likewise, the height of the paraboloid represented, this is the actual imaginary paraboloid, represented by this orange curve, dust curve. It is equal to 0.0005589 omega square r square. And this formula is derived in my lecture video on rotated vessels, where omega is in revolutions per minute automatic. So substitute R is radius of the vessel is 1 meter and omega is 152 revolutions per minute. So H is 0.0005589 square, 1 square. So H is 12.91 meters, which is greater than 8 meters. That's why the actual curved surface is this orange surface. So it is now drawn here, and we will call this Y1. Since no liquid is spilled because the vessel is closed, we equate the volume of air final, which is represented by this imaginary paraboloid with 2 radii. The radius at the top is denoted by r sub t, and the radius at the bottom is r. And the radius of paraboloid evolution with 2 bases, that's the general formula, is pi over 2, then height or distance of the bases, which is also the height of the tank, big H, which is 4, times quantity, r sub t square plus r square. And we equate it to the original volume of air, which is this right circular cylinder of height 1 meter, k, pi, radius 1 square times k, which is 1. So pi over 2 times quantity 4 times r sub t square plus r small r square equals pi 1 square times 1. Cancel out pi, then r sub t square plus r square equals 2 over 4, or 0.5. So r sub t square plus r square equals 0.5. Then we enforce the squared property of parabola y1 as to r square equals y1 plus 4 plus h as to rt square equals h 12.91 as to 1 square. So y1 as to r square equals y1 plus 4 as to r sub t square equals 12.91 as to 1 square. Then we replace r sub t square, which is 0.5 minus r square, into this equation. And from this equation here, we say that r square is y1 divided by 12.91. So y1 over r square equals 12.91 y1 plus 4 over 0.5 minus r square equals 12.91. So that means small r square is y1 over 12.91. Then we substitute back into this equation here. So y1 plus 4 as 2.5 minus r square, and r square is y1 over 12.91 equals y1 over 12.91. Canceling out y1, and the right side of the equation becomes 12.91. So y1 plus 4 over 0.5 minus y1 over 12.91 equals 12.91. Cross multiplying, y1 plus 4 equals 0.5 times 12.91 minus y1. So y1 plus y1 is 2y1 equals 0.5 times 12.91 minus 4. 12.5 times 12.91 minus 4 divided by 2. So we can now solve y1, and y1 equals 1.228 meters. So that's the answer to for part A. The maximum pressure that can develop within the vessel, it occurs around the periphery of the bottom, and it is just 100 kilopascals. The pressure, which cannot be destroyed, it is transmitted equally into the space within the tank. So 100 plus specific weight of water times this depth here. This depth here around the periphery, the deepest value of all points on the base is equal to specific weight of water times quantity H minus y1. And since we already solved y1, so the maximum pressure at the base, which occurs around the periphery, is 100 plus 9.81 times quantity H 12.91 minus y1 1.228. So the maximum pressure is equal to 214.6 kilopascals. The exposed area of the bottom, and that is the area of the circle here, pi r square, and since r square is y1 over 12.91, it is just pi times y1 over 12.91, pi r square, area of the circle. So area exposed is pi times y1 1.228 over 12.91. So that area exposed is equal to 0.2988 square meter. The next, the force on the top cover. The force on the top cover is equal to pressure 100 times area of the top cover, which is pi 1 square, plus the weight of imaginary water above the top cover. And that weight of imaginary water is equal to the weight, weight is equal to specific weight of water times volume above the top cover. The volume above the top cover is equal to the volume of this right circular cylinder of this height, and the height is h 12.91 minus y1 minus 4, then minus volume of this imaginary air above the top, which has two bases, one of radius 1 meter and the other of radius r sub t, which can be solved because rt square is 0.5 minus r square, and we have found r square already. And we will call the volume of imaginary air above the top cover as V1 as shown. So volume above the top cover is equal to volume of right circular cylinder of height equal to this. And this height, as I said, is 12.91 minus 1.228 minus 4. And that height is equal to 7.682 meters. Again, that 7.682 is 12.91 minus 1.228 meters minus 4. And this V1 here, which is imaginary air, is pi times height 7.682 over 2, volume of paraboloid of revolution with two bases, pi over 2 times height 7.682, quantity radius at the top square 1 square plus radius at the bottom square, which is r sub t square. So R sub T square is 0.5 minus R square, and R square is 1.228, or Y1 over 12.91. So R sub T square is 0.4049 square meter. So substitute V1 equals pi times 0.7682 over 2 pi over 2 height of paraboloid, quantity 1 square plus square of the bottom, which is 0.4049 R sub T square. So V1 is 16.95 cubic meter. Therefore, the volume of water, imaginary water, above the top cover can now be computed. It is just volume of a right circular cylinder, circumscribing right circular cylinder, pi 1 square times 7.682 minus V1. So that volume is equal to 7.184 cubic meters. So finally, we can compute the force at the top, which is pressure, this is constant 100, times area of the top cover, which is area of a circle, pi 1 square. Then we add 9.81 times 7.184, the volume of water above the top cover. So force on the top is equal to 384.6 kilonewtons. While the force at the bottom is simply force at the top, because the force at the bottom supposedly is pressure, 100 times area pi 1 square, plus the volume of water above the top up to here. And since we have already computed the volume above the bottom rather, we already computed the volume above the top. We only consider the volume above the bottom and inside this tank. Now, common sense suggests that that volume is supposedly the original volume of water inside the tank, which is pi 1 square times the depth, which is 3. So therefore, pi 1 square times 3 is 3 pi cubic units. But let me compute it using volume of paraboloid with two bases of radii R sub T and R, to show that that volume is indeed 3 pi cubic units. So although it is expected that that volume inside the tank above the bottom is equal to the real volume of water inside the tank, but I will still use that formula with two bases just to show and to let you convince that that formula is really correct, although I derived that in my in the lecture video on rotated vessels. So I'll call that volume of water 2. So force at the bottom is equal to force at the top, 384.6 plus 9.81 times volume of water sub 2. So force at the bottom equals 384.6 plus weight of water above the bottom and inside the tank, weight of water sub 2, and this is 9.81 times volume of water 2. So gamma of water times volume of water 2. That volume of water 2, which is expected 3 pi cubic units, as mentioned earlier, the original volume of water inside the tank. But I'll show you that it is 3 pi using the volume of paraboloid of revolution with two bases. So I'll call that volume of water 2 equals pi 1 square times 4, volume of the right circular cylinder minus volume of this imaginary air paraboloid of revolution with two bases, R sub T and R. So R sub T square is 0.4049, R sub T square, then R square is Y1, 1.228 over 12.91. So this is 4 pi, volume water 2 is 4 pi minus pi, so it is indeed 3 pi cubic meter as expected, and as I explained it a while ago. So therefore, force on the bottom is 384.6 plus 9.81 times quantity 3 pi. So force on the bottom, therefore, is equal to 477.1 kilonewtons. So that's it for this video to shorten it.